Hi, my name is Jerry. This is my YouTube channel where I make things, and if it feels like this video is a little bit rushed, that's because it is. Right now it's like the night before this video goes up, so I'm like really low on time. And while I've put plenty of time towards this project that I've been working on, and it's done and ready, I have demo videos, I have B-roll, I don't have any narration or progress updates for the build process. So here I am to tell you the story of how I actually made the project. But enough stalling, let's just jump right into it. In this video I'll be making a machine that draws art for me. But to be more precise, I'm going to be trying to spend as little money as I possibly can to build something called a polar graph. Now, if you've read the title, you can probably guess that a polar graph is a type of drawing machine, and I'll get into specifics about what makes a polar graph different. But first I want to talk a little bit more about what I mean when I say a drawing machine. Now, just to be clear, I don't want to make something that's really simple and fully mechanical, like a spirograph that uses gears, or something else that uses levers or pendulums just to make art with like dripping paint or markers or something. I want to build a machine that is computerized. It follows a digital design that you give it and it tries to recreate it. Now, on the other side of the coin, I don't want to make a perfect printer. You know, most of us already have an inkjet or laser printer, something that can print something off a computer screen to near perfection. But I find that type of printer kind of boring. You just make something on the computer, you press print, and there it is. At no point while you're working on the design do you need to think about what the printer is going to do. It's just going to magically print out the document as you give it, with like minimal artifacting and color differences depending on the printer. What I think is more fun is to work with a machine that adds constraints to your designs. Think about it like this. Whenever an artist wants to bring something into real life, they're working with tons of constraints, whether they put them there arbitrarily or if it's just part of the art process. After all, we can't just take ideas in our heads and immediately pull them out into the real world. If we could do that, I wouldn't be sitting here taking several takes of this video. We're limited to what we can work with, our bodies, our hands. I mean, for me, that's most of it. So, like a painter will work with their hands to try to recreate what they have in their mind, and working with that paint is a constraint. You're limited to the colors that you have, you're limited to the brush sizes you have, you can't go off the canvas, at least not easily. And another good example is people who make cartoons. Whenever you're animating a cartoon, you're generally limited to a small color palette and flat shading. You can't do lots of really fancy color transitions. And another one that some people do is stippling, where you try to make an image using nothing but little dots. So getting back to the project, I want to make a drawing machine that you can make digital artwork for that adds constraints. So as you work on the artwork, you have to consider what the machine is actually going to do. And beyond that, I want to make the machine kind of clunky and slow, but also fun to watch. So not like a modern inkjet printer that's just trying to print as fast as it can and as precisely as it can. I want to be able to just send a file to this machine and just stare at it for the next 30 to 90 minutes as it slowly puts that artwork together, thereby turning the creation of the physical media into a performance art of its own. So to solidify the idea, I'm thinking that I want to combine just a pencil and paper, and two motors and a microcontroller, and that microcontroller will drive the motors in order to make the pen draw dots, lines, curves, and eventually full documents on a piece of paper. Of course, what I'm describing already exists. It's called a pen plotter, although it's usually just shortened to plotter, and it dates back all the way to the 1950s, although it would later become more popular in the 70s. Back then, inkjet and laser printers were not really a thing yet, so you were typically left either using a dot matrix printer or a pen plotter. And while dot matrix printers could do graphical applications, they couldn't do it very well. They were usually just delegated for printing text. For anything high fidelity, you'd need to use a pen plotter. Of course, plotters are limited to just doing line art, but for a lot of people that was fine. As I understand it, a lot of the stuff that was printed with these things were technical drawings from CAD models, and those were already in the form of line art anyway. Now, with lots of people using these pen plotters, there were companies that actually manufactured them, and as time went on, companies like HP and a few others made pen plotters with lots of extra bells and whistles, like the ability to change the color of the pen partway through printing by physically swapping out the pen. And on the other side of the spectrum, they were able to make some cheaper ones that just moved the paper back and forth from one axis and moved the pen back and forth for the other, both increasing speed and reducing cost. Of course, the era of the pen plotter wasn't going to last forever. Once inkjet and laser printers started to become more affordable, it really didn't make sense to buy a pen plotter anymore. Newer technologies could do everything the pen plotter could do, and a lot more. So as time went on and inkjet and laser printers continued getting cheaper, pen plotters started to get discontinued by their manufacturers in favor of newer printing technology, and pen plotters just kind of disappeared. Today, pen plotters, at least the ones from the 1970s, really just exist in people's really niche personal collections of old computer stuff. Of course, the story of the pen plotter wasn't over by that point, and I'll tell you why. After inkjet and laser printers took over the 2D printing space, we saw a new technology emerge, 3D printing. Or to be more precise, the mass production of consumer-grade FDM 3D printers. Now I bring this up for three reasons. First, I want to introduce you to my PrinterBot Simple Metal in the background. Without it, I could not have made this project. The second reason is to make a bit of a bold claim. I say that any modern 3D printer is just a pen plotter with extra features. I mean, if you think about it, a 3D printer can move along an x-axis and a y-axis, and it can draw out of plastic. Now, once you add the ability to lift the print head off of the build platform and you replace the pen with an extruder that can print out in plastic, well, then you've got what I'd call a three-dimensional pen plotter. And I know the terminology is getting weird. But when you combine that with software that lets you slice up a model into individual layers, you arrive at a machine that can make a 3D version of pretty much anything that you send it. So that brings me to my third reason why I'm bringing this up. And that's that 3D printing has just exploded in the past like 10 to 15 years. I remember, I think somebody in Facebook around 2010 or so sending me a Pinterest link, and in there it was talking about the RepRap project, the 3D printer that 3D prints more 3D printers. And I looked at it at the time, and it seemed expensive and difficult to try to make one. Trying to source the parts would be difficult, and the costs would be expensive. But not too long after that, you could pay a measly $1,000, it was definitely a lot at the time, and get a professionally made 3D printer that's just ready to go. Pull it out of the box, plug it in, and then you're making objects. Of course, my 3D printer is not on either side of the spectrum. It's not full DIY, and it's not a really professional, really expensive version. I bought it as a kit back in 2015, and I paid $540 for it. And with that, I also got a spool of filament. Now, $540 certainly wasn't cheap, but given the community that this printer had and how well it was built, it certainly wasn't a bad deal, and it had lots of bells and whistles that a lot of printers in that price range did not have. But if you fast forward to today, 9 years later, if you look up a 3D printer on Amazon, you'll find dozens of different options that are usually cheaper than mine, faster than mine, larger than mine, perform better than mine, and have better bed leveling than mine. Oh, and it has a heated build platform that mine probably could have had if I bought it like a year or two later, but I mean, what can you do? But I mean, you can spend less than $200 and get like a functioning, not that bad 3D printer. You pay up to $250, you've got a good one. Now, I promise I'm not mad. Even though I paid a lot more for my printer than I could have if I waited to buy it until now, this printer has been incredible. And I'd say it's definitely paid for itself, just satisfying my curiosity trying to make things over the years. But the reason I bring this up is that as the cost of 3D printers has gone down, the parts have also gotten cheaper and easier to find. Of course, that includes the motors, the belts, linear rails, and all kinds of equipment that used to be really niche, but you can just find on Amazon now. So given all of these cheap and readily available 3D printer parts, why doesn't somebody try to combine all of these parts and make 2/3 of a 3D printer? You know, the modern day pen plotter. But a couple companies actually have. If you look up pen plotters on Amazon today, you'll see a couple of different options. Lots of them are very expensive because they're meant to print on like a poster-sized sheet of paper. But some of them can get closer to affordable at around $100. But what's common across all of them is that they use the same parts as 3D printers. Like the incredibly common NEMA 17 stepper motor, the really common GT2 timing belts. Some of them are using V-slot aluminum extrusion and the special grooved wheels for linear motion. Some of them are using linear rods and bearings. Some of them could use actual proper linear railings, but I haven't seen one that does. Now, out of all of these designs, my favorite is this one that's only $100. Because it's only $100. This specific listing is a clone of the AxiDraw, which is a pen plotter from a company, Evil Mad Scientist, and they've been working on pen plotters and software to run them for quite a while now. Now, I kind of want to get this design that's only $100. It's not too expensive. And I think if I sourced my own parts and used 3D printing wherever I can, I might be able to shave a few dollars off of that. But my goal is to spend as little money as I can in this project. A little bit of the justification, I'm not going to go too deep into my finances, but I normally like to maintain a small emergency fund in case of an emergency, and there is an emergency and that emergency fund is gone. It should recover within like 2 or 3 months, but until then, I'm just keeping my budget a little bit low so I have a little bit of extra money in case of another emergency happens. So I am fine. I have access to more funds if I really need them. I just don't want to pull anything out of savings if I don't have to. But getting back to the project, I think I can go a lot lower than $100 if I change up the design, if I think outside of the box. And I mean that literally. Nearly all of the pen plotters that you can get on Amazon today use a Cartesian motion system, which means they have one axis for the x-axis, one axis for the y-axis, and then those combine to form your degrees of freedom to be able to print on the paper. But that leads to this big, bulky, and boxy design where you have to use these linear rails to make everything slide nicely. And those linear rails can get expensive pretty fast, especially if you're making a really big plotter. In fact, the one that's $100, I don't even know if it's big enough to print on ordinary printer paper. The original AxiDraw is, but I don't know about this clone. I don't have the specs in front of me, and I'm not taking the time to go look. So if we're not going to use the same boxy Cartesian movement system, what else can we use? Well, the answer is kind of weird. We can use string. So here's the idea. We're going to take a backing board, and to the top 2 corners of it, we're going to attach a piece of string. This is pretty basic so far, but if you make it so that you can adjust the length of the strings, put them through some kind of pulley, and then pull on them, then you can start getting those 2 degrees of freedom that you need to make a drawing machine. They're just a little bit weird to work with because they're no longer perpendicular to each other. Now this setup isn't particularly interesting on its own, but once you add motors to pull the strings, so you add some sort of mechanism that can hold the pen perpendicular to the paper, and you add a microcontroller to actually drive everything properly, well, then you get to an interesting drawing machine, known as a polar graph. Now if you look up polar graphs, you'll find that they're pretty common in the maker community, although I don't know that everybody's really agreed on what to call them. But they're kind of a go-to project because they're relatively simple physically, and even though the software can get kind of complex, there are free and open source options that you can use. Now, of course, there's also open source and freely available hardware designs that you can use, but I want to try to make one designed from scratch. Both I want to experiment to see if I can, and I also want to see where I can cut corners to make the project a little bit cheaper. Now you're already getting a pretty good cost savings when you just get rid of the linear rails from a Cartesian system and instead use string, or much better, the GT2 timing belts or ball chains like you'd find dangling from a ceiling fan. But there's also some other areas where I think I can cut the costs by replacing parts with cheaper alternatives. And the first thing on the chopping block is the motors. Most people that make a polar graph want it to be good, so they'll use NEMA 17 stepper motors. They're the golden standard in 3D printing and CNC machines, laser cutters, some vinyl cutters, and a lot of the professionally made pen plotters. These things are fantastic. They're really strong, they're very fast, and they're pretty precise. And better yet, they're actually not that expensive. You can get them for around $10 to $12 each. You can get relatively cheap controller boards for them, and it only costs about $10 to $15 to get a 12-volt power supply to run them, but if I'm going to operate it in my bedroom, I'm going to spend a little bit more money for the silent stepper motor drivers. That way I can still sleep at night with this thing running. And when you add up all the costs of the stuff associated with that, it gets up to around $30, which it's still not a lot of money, but I can cut it significantly. So instead of using NEMA 17 motors, I'm going to use, actually I have to look at my notes to remember how to say this, 28BYJ-48 motors with ULN 2003 driver boards. Yeah, I can't memorize that either. Now these things might be small, but here's all the stuff that makes them better than a NEMA 17 stepper motor. And here's all the things that makes them worse. They're much slower, they're much weaker, and they have this thing called backlash. Basically, the stepper motor isn't a complete stepper motor. Only half of it is a stepper motor on the bottom, and the top is a gearbox that slows down the speed of the motor to something more usable and with enough torque that you can actually do stuff with it. But every contact between a pair of gears and that gearbox is not perfect. It can wiggle a little bit. So when you finally get to the output shaft of that motor, it can wiggle quite a lot for a project like this. If I were to put a large spool of string on it, that backlash is going to be like a good ½ inch or so. Now with all these downsides, why would I still use these stepper motors? Well, for one, they are frickin' cheap. Side note, I'm not going to stay family friendly this entire time, I reserve my right to say fuck. But these things are like between $2 and $3 each, depending on where you get them, and they come with the driver board included. And they draw enough power that you can sometimes get away powering them just through a USB port. And that problem with the backlash, it is definitely going to be a problem if you're trying to use this motor in a 3D printer. That would be a stupid idea. But in the case of the polar graph, you're going to be having the motor supporting a pin. And the weight of that pin is going to pull that motor in one direction. And in theory, that force should keep the backlash towards one end of its range of motion. And I can tell you, because I've already done this, it's actually shocking how good these motors are in that use case. Now moving right along to the microcontroller, which is going to be the brains of the operation, there's a little bit of cost that can be cut there. A lot of people will use specifically an Arduino Uno for this, and you can get those for pretty cheap, and I have some laying around, but I just don't think it's the appropriate microcontroller for this job. Particularly, since it allows you to put power through either the USB port or an external battery through a power jack, any power that you send through the USB port has to go through a power supply system, and that is not rated to handle a lot of current. So it is very much not recommended to try to power motors through an Arduino Uno's power supply. Of course, if you're using the NEMA 17 stepper motors, they're using external power anyway, so that's not a problem. But I have to consider the motors that I'm using. And the other issue is the amount of space available on the Arduino Uno. It has a whopping 32 kilobytes of space available on it, and part of that goes towards the bootloader so it can turn on. Part of that goes to the Arduino core that handles interfacing between the code that you write and the hardware-specific stuff on the Arduino Uno. And lastly is the code that you write, which just kind of gets slotted in at the end. Now you still have good like 27, 28 kilobytes of space to put stuff, but in terms of storing a design, that's really not that much. So if you're going to use an Uno, you typically have to make use of some other way to get the design to the microcontroller. So you could use an SD card, which is not too expensive, or you could just leave it plugged into a computer, and the computer can send the commands over the USB port. But I really want to keep the cost down and be able to put designs directly on the microcontroller. And for that, I'm using the ESP32. Specifically the classic one, not the S, S2, S3, C3, C6, or any of the other modern ones. Because of how old this is and how common it is, you can get it for around $5 each, and it's got 4 megabytes of space. Which, again, is not a lot, but I believe with the right code tricks, I can fit a design with about 500,000 points in it. And that should be plenty for a quote-unquote cheap pen plotter. Next up on the chopping block is the strings. And I'm obviously not going to use household twine, that's not going to work well because it's stretchy. And I could use GT2 timing belts or the ball chain off of a ceiling fan, but instead I'm going to use this fishing line. Not because it's superior to anything else, but just because, well, I already have it. I was walking through the clearance aisle of Walmart one day, saw this, and I was like, I could use that in a robotics project. And what I had in mind was going to be more so 3D print a fake spider and just slowly have it descend on the fishing line, but this works too. In the future, in addition to fishing line, I'm probably going to try upholstery thread. That was another suggestion I've seen online for this type of thing. And the last thing I'm going to try to reduce cost on is the backing board. A lot of people will just go to Lowe's and get the cheapest piece of plywood they can find, or particle board, MDF, something. You could also, if you wanted to get something that looks a little bit nicer, you could use a whiteboard or a bulletin board. Instead, I've opted to use a $1 foam board that I found at Walmart. The same one that I did the demo with a few minutes ago. Well, actually, that one was my spare one. The original is covered in lots of test marks. Now, the last thing on the chopping block, and I might be saying the last thing twice, I don't remember what I just said for the backing board. I just remembered this. All of the extra stuff that you need to make a project like this. Screws, nuts, hot glue, any random stuff that you'd have laying around, because, well, I have it laying around. I'm going to just use what I have. For instance, screws and nuts that were left over from an engineering project back in high school, magnets that were left over from a project back in high school, plastic beads that have nothing to do with high school, binder clips that also have nothing to do with high school. I don't know why I keep saying this. Jewelry making supplies that I bought, honestly, just last year to make some keychains. And one mystery supply that I think genuinely saved the project. I'll talk about that later. Also, I lost my train of thought. I just had to plug in the camera because it was running low on battery. But now we can finally start talking about the building process. How far are we into the video and I haven't actually made anything yet? It's kind of embarrassing. Also, I'm going to have to heavily reference my notes. I've been building this project over the past 3 weeks, and my memory's a little bit fuzzy at this point. And this is why I check my notes, because I forgot that the first thing I 3D printed for this project has nothing to do with the project. I was in Goodwill several months ago, and I picked up a board game, Sorry, and it was taped closed, so I couldn't check if it was missing any pieces, and miraculously, it had everything. Except for the blue pieces. I don't know why it's only the blue pieces that were missing, but seeing as I have blue filament laying around, I decided to 3D print replacement pieces and test out my modeling skills to make sure I could still use FreeCAD. Also, side note, this video is not about 3D modeling, but I just have to say, if you want to get into 3D modeling, even though I really like it, I highly recommend that you do not try FreeCAD as your first 3D modeling tool. It is an absolute nightmare to use, and I only put up with it because it's the only free and open source option. All of the other ones use MacLeod, they have ever-changing license agreements, it's annoying. But learn with those and then jump over if you really want to. Anyway, I got these Sorry pieces modeled, they were relatively easy, and I sent them over to the 3D printer, and the first two came out honestly not that great. But they're usable. But take a look at the second two. They're somehow even worse. They make the first two actually look really good. Now, a lot of the problems with these are specifically due to my printer being out of calibration. I haven't calibrated it in years. And to this day, I still haven't done it properly. I'm kind of scared to touch it because I can't buy any parts for it. A lot of the documentation for it is kind of hard to find these days. It is a dinosaur. So as long as it still is mostly functional, I'm fine with it not being perfect. And really the biggest two issues with these pawns are that it over-extruded at the top of the pawns because it was doing solid infill. I know I'm getting a little bit too technical here, but hold on. And the other issue is that the bed adhesion wasn't good. And I had a lot of problems with that later on, and I was able to fix it just by increasing the temperature of the first layer. And after that, things were turning out mostly okay. So once I proved to myself that my 3D printer could still function without catching on fire, I started testing out some mounts for the motors, or more specifically the motor shafts. At first, I just printed these little tiny cubes with holes in them so I could make sure I could get the hole the right size for the motor shaft without printing anything larger. And once I got those numbers dialed in, I moved on to make a universal mount that I could attach any size, any design of fishing line spool that I make in the future, because I figured I'd be iterating on that a bit, and I didn't want to have to print the entire thing every time. Onto that universal mount, I would attach a 2-part spool, printed in 2 parts just so I don't have to use any support material. It's better for the environment, it's better for my sanity because I don't have to spend time cleaning it. But with an entire spool successfully mountable onto the motor shaft, I moved on to mounting the motor itself onto the side of the foam board so I could test its strength. For that, I 3D printed this really flimsy, but still effective little plate that I can screw the motor onto. I ended up having to add some extra spacers, that way the motor wasn't bending the mounting plate it was on. And this whole thing clips onto the side of the foam board with binder clips. Now, with a spool of fishing line mounted to the motor, and the motor mounted to the foam board, I could finally attach a weight to the end of the string and test how strong the motor was. And what I found out was, it's honestly not that weak. It can lift a decent amount of weight, but I still wanted a little bit extra safety margin. So I reduced the size of the spool, that way I would have more leverage and it could lift about 50% more weight. Now, when I started to consider how this would work together with the other motor and the pin carriage that would hold the pin in place, I realized that the string was a little bit too far off the front of the board. So to make it a little bit more like in plane with the board, I printed another motor mount. This one having the side benefit that it is much, much stronger and well built and shouldn't bend under its own weight. And this one worked pretty well for early testing, although I was still waiting to print the other one until I got a pin carriage working. So moving on to the pin carriage, sometimes called a gantry by other people. Honestly, I don't know what the right terms are for these things. I was just really stumped right away. I looked at a couple other designs and I saw some interesting ones. There's one that I saw that I've had a little bit of trouble finding. If I can find it, I'll put a picture here, but I just pointed to my face. Did I just cover my face? Now, what I liked about the design was that it was both pretty simple and pretty sturdy by the looks of it. it formed a lot of triangles just using string, and it seemed like I could do a good job of keeping the pen perpendicular to the page. But I really didn't like the idea of trying to precisely work with the fishing line. Every experience I've had with it, it is incredibly slippery and really hard to tie knots with. Now maybe that's just me, maybe I need some more experience working with fishing line. I mean, I haven't gone fishing in at least a decade now. Now to remedy the problem that I really couldn't manufacture this string contraption out of the fishing line, at least with my skill set, I ended up trying to 3D print the same shape. And it really didn't go very well. The 3D print didn't turn out very good. I didn't like the way the design looked itself. I just still printed it because it spent like an hour and a half designing it and I just wanted to see it. But I didn't move forward with it. Instead, I tried to achieve the same idea, that you're just keeping the strings perpendicular to the pin in a different way. And I figure you can do that by taking two bearings that will allow for movement around the pin, but keep the strings perpendicular to the pin, and then just attaching arms to make sure that they're going to work properly. It is admittedly a little bit hard to explain exactly what I was thinking at the time, so hopefully actually seeing it will make more sense. But I didn't want to use actual bearings. There are some people online that do, but I wanted to use something that was a little bit bigger and a little bit cheaper. So I basically just 3D printed what's called a bushing, basically just a circle around another circle. And how does it deal with friction? It doesn't. Now I figured all of my parts would be lightweight enough that it wouldn't be a problem, but once I got a proof of concept printed and got it moving, it was giving really jerky movements when I was testing it. So I ultimately determined that the amount of friction that was happening was too much, and I did in fact need to use a bearing. But I still didn't want to rely on buying a bearing specifically for this project. So I looked online and found a person that reviewed a few different types of bearings that you can 3D print. And the one I went with is where the mystery supply comes in. As it turned... I have to hold this perfectly still, otherwise it's going to be extremely loud. But as it turns out, you can use just this plastic biodegradable airsoft ammo as the balls in a ball bearing and 3D print the inner and outer rings, and it just works. Now a bearing like that made of 3D printed plastic and literally biodegradable plastic isn't going to last long if you're using it in a real industrial environment, but for what I'm doing, it should work fine. And it's really nice because it's going to be really lightweight. Now I'd like to show you the original bearing that I printed to make sure that it would spin properly, but I quickly developed that into the final pin carriage, and I really don't want to take that apart because it is a nightmare to put together. After a couple of revisions of the bearings and finally getting this all together, I finally got this thing. So each of these arms move independently, and down here there's a little hook that I can attach a weight to, that way it keeps the pin upright. And honestly, this is pretty good. It moves very freely, and the results I was getting were not bad. Of course, this still doesn't have the pin in it yet. The pin would go through this small hole in the middle. I think it just might fit. Okay, but seriously, the giant hole is just so that there's plenty of extra room for you to see around the pin. Because if I made these bearings really small, then you wouldn't actually see the pin writing. You'd just see what it had written like a good inch or two after it wrote it. And now that I've praised this design enough, it's actually not that good. And to clarify, if I was using NEMA 17 stepper motors, this would be fantastic. It's really cool, but it's already very heavy. It's like pretty close to the amount that the motor can lift, without any extra weight to help stabilize it, and without the weight of a motor that could lift the pin off the page. I meant to bring this up much earlier, by the way. A lot of pin plotters use a servo motor. That way they can lift the pin off the page and draw multiple disconnected things, or go wait for the user to change out the pin to a different color. And originally I wasn't going to include one in my polar graph, and it's not because the motor's expensive. You can get them for like $3 or $4, just like the stepper motors. But I was a little bit concerned about the cost of the wires that go to it, because I'd need a several foot long wire, and that does actually kind of get expensive if you're making it yourself. But then I looked on Amazon for servo motor extension wires, and they're not too cheap. So I decided that I was going to add one, and adding one to this design would make it even heavier than it already is. So at this point I had two options. I could either make my motor stronger, or I could make the pin gantry lighter. Now making the motor stronger is actually not as hard as you would think. I can just reduce the size of the spool again. That'll give it, yet again, more leverage and more strength, but it will make the plotter slower. And it's already pretty slow with a top speed of around 20 millimeters per second, or less than 1 inch per second, where the axi draw, it's like 10 or 11 inches per second at its maximum. And another route that I could go is to add a counterweight, just a weight on the other side of the spool that helps reduce the weight that the motor is applying. But because polar graphs are really weird, sometimes the weight that the pin is exerting on the motor is going to be more or less than the counterweight, which means that sometimes the motor will be pulled left, and sometimes the motor will be pulled right, and if you remember back to the conversation about backlash, that's a bad thing. So with both of those options not being great, I ended up scrapping my idea for the pin gantry and starting over. Of course, I actually kept the bearings, they were really good, but I made the hole in the middle a lot smaller, so no more fitting the comedically large Magnum Sharpie into this pin plotter, and more frustratingly, you're not going to be able to see the pin as it writes on the page. But it should actually be able to write on the page now, so I guess it's a trade-off that's worth making. Oh, and this time I can actually show you a build video, because I thought to record me assembling this new one. Starting out, you have the base plate, which I call the stabilization plate. There's a little tiny spacer, that way it just gives a little bit more room before the first bearing. The bearings themselves, you can now finally see how they're made, very slowly and carefully. Then you sandwich two of those bearings together on the screws. On top is just a little plate to keep the nuts in place and add these little pegs that help align where the pin attaches. And again, you get to see it this time, because I've included that in the video. A little nut goes into the top hole, and then you can put a screw into the side that you can tighten down the screw onto a pin, and then a pair of magnets on either side will hold it down onto the actual pin gantry. Also, I finally dialed in the tolerances for these bearings. They are fun to spin now. It's like a fidget spinner, but like way too late. And they do have a little bit of play in them, so precise applications they're not going to be good for, but the amount of play that they have is like not that bad for what I'm doing. You'll also notice the two holes at the bottom of the stabilization plate. That is for the servo that's going to lift the pin off the page, because I actually did add that. And I'll say right now, I originally started out with this elliptical little disc thing that goes on top of the servo, just because the actual servo horn, little white thing, wasn't long enough on its own. But what I found is that that disc, because it's flat on top, will catch onto the bottom of the piece of paper and will like rip it up to shreds. So I'll end up redesigning that part to this little finger-looking thing after a few prints. And that smooth surface on the edge will help it glide onto the edge of the paper without getting stuck. Now, while all of this was going on, I was kind of doing some mathematics in the background, trying to figure out how big of a page I can fit in this pin plotter. And it really depends on a lot of different factors: how strong the motors are, how heavy the pin gantry is, if I'm using counterweights, how that's going to affect the backlash. And ultimately what I determined is that if I want to print big stuff, I need to have the motors further apart than what I'm able to get with this foam board. But you have to remember, this plotter is going to work best when the strings are at a 90-degree angle against each other. So just rotating the foam board so it's horizontal instead of vertical isn't going to give me all that extra distance that I need in a usable way. Now, I was originally planning on getting a couple more foam boards so I could stick two of them together. But when I went to Walmart to go purchase more, they were out. Well, mostly out. They still had two, but they were absolutely destroyed. Now, they had the ultra strong foam boards, but they're like $3 each, and I don't need it to be ultra strong. And yes, I know the irony that they're the only ones that survived, the cheap ones didn't, but I don't need it to be strong here. The board that I have is fine. I just need it to survive getting to my house. So with a new foam board out of the question, I went a couple aisles over and started looking at big old whiteboards and bulletin boards. Kind of going back on my plan to keep the backing board really low cost. And after looking around, I left the store with this. This is a bulletin board with like a corkboard backing. I've just taped a poster to the front of it so I can make marks on it without them being permanent. Of course, with a change of the backboard, I had to redesign the motor mount yet again. This one's actually really solidly built, more so than all the other ones, and it really holds its place. Now with the backing board replaced with something bigger and more sturdy, and the pin carriage mostly functional, and the motor mounts mostly functional, I was finally ready to actually connect both of the motors at the same time and test out what this thing can do. Well, almost. I was still just plugging one motor at a time directly into the ESP32, and I can't do that with two of them at the same time, and trying to connect the servo along with that too makes things even more complicated. So I ended up taking some perforated circuit boards and soldering those together with some ribbon cables, and I added a few buttons as a remote, and I finally get this big old cable loom that connects the ESP32 with both the motor controllers, and I can simply pull it apart if I want to use those parts elsewhere. Also, not important to the video, but I did manage to burn myself with a soldering iron. I think that was like the first time that I really did. It is a week later, and it is still scabbing over. It is crazy how long it is taking this to heal. But back to the project. I finally had everything I needed to actually do a test print. And here's how it went. Now, I'm going to be perfectly honest, I don't remember if I filmed myself making this or not, so whether you're staring at a photograph or a video, the first thing that I made was just a small grid. And that was just to make sure that the motors were moving properly, and to show off one of the ways of many that a polar graph is weird. Because the x and y coordinates that form that grid translate into this weird skewed object where the corners aren't perfect right angles, the lines aren't straight, and the whole thing is at a 45-degree angle. And if you think this one's bad, I printed the same thing, moved the carriage up before it started, and again moved it down before it started, and these are so much worse. Now the good thing is, I was expecting this. Polar graphs are weird, you have to compensate for that in the code that you write for them. So there are ultimately 3 solutions that I implemented to make this work better. The first one is inverse kinematics. The easiest way to explain inverse kinematics? I have a point in space, I want to put my finger there. Inverse kinematics takes the real-world coordinates of that point, x, y, and z, and figures out what angles my elbow, shoulder, finger, hand, everything needs to be at to get to that point. In the context of the polar graph, inverse kinematics means we need to figure out what position each motor needs to be in order to get the pin to a certain spot within the design. Now, in order to get inverse kinematics working, I had to solve some mathematical equations to figure out what position the motor needed to be in, and I'll briefly explain that mathematics now. Trigonometry. So the next step that I had to figure out was getting the lines to move, well, in straight lines. I should be like actually figuring out where do these motors need to be part way along the line so that the line stays straight. And what I've just described is, in a way, interpolation. What does the machine do in between point A and point B? Now with the grid I just showed, it tries to go straight from point A to point B, but because of the way a polar graph is, that line is not straight. So my method of interpolation here is whenever I need to go from point A to point B, I instead go to point C, D, E, F, G, H, I, J, K, so on, until I finally get to point B. Now if those individual line segments are small enough, they're still going to be curved and weird, but it's going to be on a small enough scale that you don't notice. And the last thing is, well, if the design looks so much different, depending on where the pin is on the page when it starts, I need a way to tell the microcontroller where the pin is. That way it knows where the design needs to go, and it can compensate for the weird polar graphiness of the mathematics. Now to solve that, a lot of 3D printers and the classic Cartesian pin plotters use homing sensors. Usually just a little switch that gets pressed whenever it hits one end of its range of motion. And that concept could apply to the polar graph. I could make some weird little cage thing that goes around the spool and detects when the pin carriage crashes into the spool, but I don't like that solution. It's expensive, it's complicated, I don't want to do it. So I created a manual homing procedure. Basically, I use the little remote to drive the pin directly over a mark that is at a known location, and when I'm done moving the motor, the microcontroller will know exactly where the pin is and how to move from there. So somewhere right here on the board is a little tiny dot, and I line up the pin carriage to that. And again, because polar graphs are weird, vertical movement in this range is amplified because it's so high up on the page. So to finish that calibration, I also move it vertically to match the bottom of the paper that I'm printing on. And now, with all of the software solutions figured out, I can finally show you what I made this machine draw. Almost. I promise we're close. I've got wonderful time lapses. I got plenty of designs for you to look at. Just hold on with me for 1 minute, because I got to tell you about this last physical design change that I did after doing some test prints. Basically, I just noticed that the prints were coming out a little bit wobbly, and I traced it back to the spools. The spools themselves were wobbly. So upon closer inspection, I noticed that this universal mount that I made for the spools, well, after a week, it had started to stretch out, and it caused the entire spool attached to it to get wobbly, and I ended up redesigning it and reprinting it twice throughout this testing period. And I used this first modified universal spool mount to print one design, and it was so much worse. So I redesigned it again, taking into account what the 3D printer was going to do in the slicing software. That way this new design was a lot stronger, and that one has made it into the final design, but it also makes the spools a little bit different. This final one's a little bit skinnier, which means I have to put a spacer on top of the spool, makes the spool closer to the board, which is like kind of good. Anyway, that's the final revision. Let's finally take a look at what this thing can do. Hopefully I'll add in some music or something, but we'll see how this goes as I read off my notes. So, on to the first design. As you can probably imagine, this first one is just going to be that grid again. Except this time I've made it bigger. I'm actually printing on tabloid-sized paper. This is twice as large as printer paper, because I think it looks cooler. The quantity that I've purchased also cost me $30, which means I've spent almost as much on paper as I have on all of the electronics for the rest of this project. And in this design, you can already start to see the wobbliness near the top of the page that's due to that spool being a little bit crooked. And as this continues, I have to say, this is still not printing off of an actual file. This grid is being generated with some for loops, basically just some fancy code on the microcontroller itself. I can change how big the grid is by changing some numbers, but otherwise I have not yet prepared the code to print a design from scratch. So that's what's coming up now. I ended up basically drawing out something in Inkscape, which is a free vector graphics editing software. I saved it to a file, and I opened that file in Notepad. And from there, I was basically just able to copy the coordinates of all the points on that path and paste it into one big list. And here's how that first attempt turned out. So it's safe to say this wasn't the intended behavior. I forgot to multiply a number by 2, so it was reading the coordinates wrong. But since I had to take a few minutes to reset the paper and restart the drawing, I'm making you take 30 seconds to look at my failure. Now here's that same print again. I just fixed the issue, so this time we'll actually be able to see what it's supposed to look like. And full disclosure, it is traced off of a graphic that I found online. Of course, in the future, I really don't want to be tracing artwork to put on this printer. I want everything I make, particularly anything that I give away or sell, to be original, or at the very least clearly communicated where that art is from. And I will tell you exactly where this graphic is from once it's done. If I tell you now, it'll spoil what it is. But the other thing I want to point out with this is that pin lifting motor, it's still not plugged in. This entire trace was done using a single path. Anytime that the pin would normally lift off the page and go to another point, I've instead manually made it follow back through a line that is already drawn to get to that new location. And since this design was mostly already connected, all the lines were already attached to each other, this actually worked pretty well. Okay, I don't have my microphone set up, I don't have my lighting set up, I really need a shower, I have to show you. This is incredible. I'm amazed at how well this machine is doing at $50 in parts. I could not have predicted a result as good as it's giving right now. It's just crazy. If you can't tell by now, this is the James Webb Space Telescope, and it's made from a graphic released by the Space Telescope Science Institute. And like I said earlier, at least I think I said this earlier, I don't really want to trace artwork. In this case, it's special because this artwork is in the public domain. Because this institute is partnered with NASA, all of their stuff by contract has to be released to the public domain. So moving on to the next design, I wanted to test something that would really push the limits of how precise the pen can be. So what you're seeing right now is called the Hilbert's curve, and if you haven't seen it before, then go look it up. It's very interesting. It's a space-filling curve. The very simplest version of it only has 4 points, but as you go to higher and higher degrees, it fills in more space. This, I believe, is a degree 7 Hilbert's curve. And once again, that pin lifting motor is still not plugged in. I'm just manually dropping the pin at the start, manually lifting it at the end. Otherwise, it's all one line. Another interesting factoid about this design is that at this point, I was still moving designs from my computer to the ESP32 by literally copying and pasting out of the SVG file. And that started to pose some very glaring issues. The entire reason that this Hilbert curve is at a 45-degree angle is not an artistic choice. When I tried to export it when it was vertical, the SVG format actually has a special command for vertical and horizontal lines, and I was not prepared to deal with that when I was copying the data over. So after this design was done being drawn, I worked on a Python script that would open up an SVG file, it would look for a single path, and it would actually properly interpret all the commands that the SVG paths use and convert them to a format that'll work with the ESP32. Coming up now is the first design that I think is classified as original artwork. This is, again, the Hilbert curve, but this time I've warped it into the shape of a building, as you'll see. This is also the first design that was printed from the SVG file using the Python script, and it turned out pretty well. Additionally, this is the first design where I had the pen lifting motor installed and working. Even though this design is still only one line, it can automatically start and stop that line. That way I don't have to babysit it towards the end of the drawing and manually pull the pin out once it's done. This next one should be kind of interesting. It is a photograph of the thing that causes 99% of the problems in my life. This design was made by a program called Squiggle Draw, and it's basically just a whole bunch of little squiggly lines that go across the page. It's provided through a program called Processing, which I've used before for other projects, and it allows you to import an image, make adjustments to how the lines are going to look, and then export the result as an SVG. That SVG caused tons of problems. It did not work with my script at all, and I ended up having to do a lot of manual editing to the line to get it to work properly with that script. I had to load it up into Inkscape, I had to remove all of the curved lines by flattening all the curves, and the scale of the design was way off. When I tried to put it in the machine, it was trying to print way off the edge of the paper. I ended up fixing that by making a new file and copying and pasting the path over. At this point, I was starting to realize that maybe making a Python script from scratch to do all these conversions on my own was not the best idea, especially since SVG files have been around for ages, and they're actually deceptively complex. You can have different groups of objects, you can have transformations applied to groups, you can have lots of weird stuff that I would have to account for if I insisted on maintaining my own Python script for this conversion. So I started looking at tools that are available online, and I found this thing called vpipe. I don't know if that's how you pronounce it. It's VPYPE, and it is a utility built in Python specifically for making pin plotter artwork. It has some nice generation tools, you can make random lines, you can make interesting patterns if you know how to use it. I'm just using it to actually prepare the files for printing. It's able to take an SVG file as an input, optimize the order in which the lines are drawn, and then export it to a standardized SVG format that I adapted my Python script to work with from that point on. And that pipeline of putting my design through vpipe and then through my own Python script to get it into a header file that I'd put on the ESP32, that pipeline stayed all the way through the rest of the project. Also, in addition to rewriting the Python file that converted everything into header files, I rewrote the code on the ESP32 that actually interprets that data. That way I can make it a little bit more useful. Specifically, I moved from using 4-byte floating point numbers to store the data, down to using just 2-byte integers to store all the data instead. Now in layman's terms, that just means that I can fit in twice as many coordinates in the same size file, and if you care, even though I'm dropping down to 16 bits of precision, that is more than enough. I can still go to within 1/20th of a millimeter with that amount of data. This new format also allowed me to add in commands in addition to regular coordinates, so I could lift the pin and put it back down at another part in the design. And another cool thing is that I can make it pause until you press the button, which means I can make it lift the pin off the page, wait for you to change the color of the pin, and then hit the resume button so you can actually have multicolored prints. And that's what's coming up next. So this design is going to be my first attempt at making a multi-line drawing, both with independent segments and with multiple colors. And right away you can see a couple problems. First of all, the word green is written in blue, and believe it or not, that is intentional. All the words are supposed to not match the color that they're drawn in. But you can also notice that the word is getting a little bit wobbly, and that's because this was as I was trying to fix the issue with one of the wobbly spools, and I remade the design to one that was worse, and it's far worse than this, and I fix it after. Anyway, by now you should see that it has started printing another word and the same color. It never actually did the color change. I had another error in my code. It wasn't inserting the pauses properly. I let it continue printing with these problems, and right at the end it gave me one more failure. you'll see that the edge of the stabilization plate gets caught on the piece of tape, which causes the entire thing to lift up off the page, breaking the line that the pen is drawing, and now there's just this massive gap in one of the letters. And to quickly fix that, I just used some sandpaper on that stabilization plate. It hasn't fixed all of my problems, but it has fixed most. Now I still wanted to test a multicolored print, so I was going to print the same thing again, but I thought that would be boring, so I swapped it up and replaced it with a quote from one of my favorite comedians.
Brayden can't eat blue foods. Apparently this kid, if he eats anything with a blue food preservative in it, he just taps out. That is bullshit. Firstly, don't call your kid Brayden. Secondly, blue is not even a natural colour for foodstuffs. It occurs very rarely in nature. Name me one blue food. Blueberries are fucking purple! I'm talking about Mentos blue, like 7-Eleven slushy blue. What flavour is that? Fucking highlighter? I know, Randy, blue means mint. Mint is green!
Now with the ability for me to lift the pen off the page, move to a new spot, and start a new line, I wanted to use that in a design that really needed it. So I made another squiggle drawing, but this time I did a little bit more pre-processing and post-processing to make it look cooler. I started out by removing the background of the image, that way you just saw the actual subject. And when I put it through the program, it still added a whole bunch of extra lines that weren't needed, so I pulled it in Inkscape and trimmed down those lines just so I have the subject. And again, I put it through VPipe. It optimized all of the order in which that everything was drawn. And honestly, my pipeline to go from design to print was getting pretty good at this point. But things are about to get so much more interesting. And another interesting fact about this design, it'll be the last one that I print in black ink, at least for now. That's not an artistic choice. It's just a few days before I started recording this video, I left the black pen in the plotter overnight, forgot about it, and the next day it was completely dried out, and I don't have any more. The other interesting fact is that it's the last design that I have to show you made with any method other than the one that I'm about to introduce. This new method is I will create a scene in Blender, 3D animation software, using lots of basic shapes, icospheres, toruses, spheres, cones, stuff like that, render it out into a PNG, and then pull it into Inkscape, and then trace all of the edges so I have a design that looks very 3D. But before I committed to actually trying that out, I looked up if I could just export from Blender into an SVG directly, and it turns out you can through an add-on called the Freestyle add-on. Also, if you can't tell by now, this is a dog, specifically my dog Rosie, who I unfortunately had to put down a couple weeks ago, but out of all these designs, this is my favorite. It's the one that's going right up on my wall once I get a frame for it. But back to this new method of making designs. The Freestyle add-on lets you basically export any edges that you want within the scene. It'll automatically figure out what edges of the object are not visible, whether they're covered up by something or if they're out of frame, and it'll let you just export all those lines in an SVG file. I end up having to run those through VPipe, that way it trims it down to the size of the page properly, and sometimes I'll do some extra processing in Inkscape so I can get the lines going in the right direction that I want. But this pipeline, going from 3D scene, export using the Freestyle add-on, process through VPipe and Inkscape to get to the final thing that I want, putting it through the Python script, loading it into the ESP32, reprogramming it so it has the new design, and letting it read off of that. That monstrosity is the pipeline that I've used for every design that I've done since. And I could walk you through how I made each scene and any of the challenges that I faced moving forward, but it's taken me so long to record this part of the video, and I knew it would, so I'm just going to leave you with a montage.